The hypothalamus sits at the core of the brain's metabolic command center, orchestrating hunger, satiety, energy expenditure, and hormonal signaling that regulate body weight. As the body ages, this finely tuned system begins to degrade. Hypothalamic neurons that once responded precisely to nutritional signals become inflamed and less responsive, contributing to dysregulated appetite, increased fat storage, and metabolic slowdown. One of the increasingly recognized mechanisms behind this dysfunction is impaired autophagy in hypothalamic neurons, a decline in the cell's ability to clean out waste, damaged mitochondria, and protein aggregates. Emerging evidence now points to nicotinamide mononucleotide, NMN, as a promising intervention that may restore hypothalamic autophagy, normalize appetite control, and help prevent age-related weight gain. Aging reduces NAD+ levels in the brain, and this drop in NAD+ has profound effects on hypothalamic function. NAD+ is essential for the activity of sirtuins, particularly SIRT1, a family of enzymes that regulate gene expression, stress response, and, crucially, autophagy. In the hypothalamus, SIRT1 plays a vital role in maintaining the metabolic flexibility of key neuronal populations that regulate hunger, including POMC, proopiomelanocortin, neurons that suppress appetite, and AGRP, a GUD-related peptide, neurons that stimulate it. When NAD+ and SIRT1 activity fall with age, these neurons become less responsive to circulating signals such as leptin, insulin, and ghrelin. The result is leptin resistance, impaired satiety signaling, and a gradual drift toward positive energy balance, even without a major increase in calorie intake. Autophagy is deeply intertwined with this process. In a youthful hypothalamus, autophagy helps neurons adapt to nutritional cues by remodeling intracellular components, maintaining synaptic plasticity, and preserving mitochondrial function. But as autophagic flux diminishes with age, damaged mitochondria and inflammatory debris accumulate in hypothalamic neurons, leading to cellular stress and local neuroinflammation. These changes are not merely side effects of aging, they are active drivers of disrupted appetite regulation and metabolic dysfunction. Restoring autophagy in the hypothalamus may be one of the most direct ways to re-establish metabolic control in the aging brain. NMN offers a route to this restoration. By increasing NAD+ levels, NMN reactivates SIRT1, which in turn promotes autophagy by deacetylating key autophagy-related proteins such as ATG7 and LC3, and by enhancing the expression of genes involved in autophagosome formation. In rodent studies, NMN administration has been associated with reduced hypothalamic inflammation, improved leptin sensitivity, and enhanced mitochondrial integrity in neurons, effects that suggest a functional revival of central metabolic regulation. Interestingly, the hypothalamus is one of the brain regions most vulnerable to metabolic and inflammatory insults, making it particularly susceptible to the effects of aging and obesity. Yet it is also highly responsive to NAD+ dependent interventions. In models of diet-induced obesity, NMN has been shown to improve central insulin and leptin signaling, leading to normalized food intake and weight stabilization. While these effects are likely multifactorial, improved autophagy in hypothalamic neurons appears to be a key mediator, allowing these cells to regain their responsiveness to energy balance cues. Beyond appetite regulation, NMN-induced hypothalamic autophagy may also impact circadian rhythms and thermogenesis, two other processes governed by this brain region and critical for healthy aging. SIRT1 in the hypothalamus regulates clock genes and temperature-sensitive pathways, which in turn influence sleep, body temperature, and energy expenditure. Aging disrupts these rhythms, but NMN may help restore them by clearing damaged cellular components and re-establishing normal neuronal signaling cycles. It is important to note that the hypothalamus is not easily accessible to most interventions, due in part to the blood-brain barrier and the specialized nature of its neuronal populations. That NMN can influence this region speaks to its broad bioavailability and systemic potential. While human studies in this domain are still limited, early clinical research on NMN has shown central nervous system effects, including cognitive and mood improvements, suggesting that the compound does reach the brain and may influence hypothalamic function as well. In conclusion, NMN appears to offer a multifaceted solution to the problem of age-related appetite dysregulation. By restoring NAD+ levels in the brain, NMN reactivates sirtuin-driven autophagy in hypothalamic neurons, clearing inflammation, enhancing hormonal responsiveness, and rebalancing the hunger-satiety axis. These improvements have the potential to prevent the slow, insidious weight gain that plagues many people in later life, not by suppressing appetite artificially, but by restoring the natural precision of the body's own energy regulation systems. NMN, in this light, stands not just as a metabolic supplement, but as a potential recalibrator of the brain's command center for aging metabolism.